In this video, we will continue with another classifier. We will continue with the support vector machine classifier. We previously saw the logistic regression. So, what is the support vector machine classifier? We will start with the. We won't be going this classifier. This algorithm has a lot of mathematics behind him, but we won't be going that much into details. We will just try to explain it with some visual examples that we have over here. So the main goal of a given classifier is to split the for example the in our case the abnormal and the normal instances with some hyperlane, for example like this red line over here, which will split the positive instances on the other side, on the one side, and the positive and the negative instances on the other side. So the goal of the support vector machine algorithm is to detect and find that hyperlane ideally. What does it mean by ideally? So that uh, it will split the positive and the negative instances. We're speaking now in terms of binary classification. It will split both of them on one side and the others on the other side with the equal distance w over here. So the goal, this is a really complicated optimization process, which represents finding the right value for w in order to draw this hyperlane and separate them on the both side. Over here, for example, if these are the positive, these are the negative instances. In this case, we have only two features, x1 and x2, and this is pretty much almost rare to happen in this is almost rare to happen in real life, to have a data set with only two features. But this is the easiest example to show. These two blue points over here and this one green point over here, they are the so-called support vectors. This is where the distance, this is the first point from the negative and the first 2 points from the positive instances, and they are on an equal distance from the hyperlane that is separating the positive and the negative instances. Let's take a look. How does that look when we have it in three-dimensional space? So the hyperlane now, it's not just a line. It's something. It's more complex. But as we can see, it's separating the red from the blue instances over here. But then we have another situation. For example, this is again a two-dimensional space, 2D space, where we have one feature on the x-axis, another feature on the y-axis. But as you can see, the real separation between the red and the green instances over here points is actually probably something like a circle. It's not a straight line. So how do we separate with support vector machines? Therefore, for that usage, we have to use a kernel function. What does that kernel function does? Sometimes it's some Gauss function or something else. There's a lot of kernels that exist. What it does, it maps each of the points into that kernel function, and now it's in three-dimensional space, as we can see over here. And now the decision surface or the hyperlane, it's much easier to detect it over here. For example, also we have this another example where the separation between the red and the blue instances is something of a curve that it wouldn't be able to be a straight line in any way. If it's a straight line, it will miss some of the instances. So what do? We elevate this two-dimensional input space into a three-dimensional input space by some kernel function, the function over here, and then we can detect the hyperlane that will separate the instances over here. So let's see how this is pretty much what the support vector machine does. As I said, this whole optimization process to find the hyperlane is quite complicated. To find the real W, which will provide an equal distance from both the positive and the negative instances, really a complicated process. So this algorithm is considered for one of the slowest ones, and it takes quite a time to achieve the results that we need. Let's see how it looks with code in our notebook with the library sklearn. Uh, so here we'll do the support vector classifier. First, we will see how to train the model. So training. In order to train this model, we have to import from scikit-learn. We have to import the SFC, SFM actually, or you can directly import SFC, which is the class for the support vector classifier. After doing that, we have to create the object of this classifier. Classifier equals to SFC SVC, and then we can fit the values into this classifier. So we can put X train, Y train. Let's see what will happen now. Um, Actually, it's svm.svc over here. Svm. Okay, but now here svm. The package in the scikit-learn library. So from the package svm, we have to import the classifier svc over here. Now we have a warning. Column vector y was passed with the one the array was expected. So we'll get the values from here. Values. And then do ravel, like it's suggested in the output. Here it is. The classifier is now defined, and the values are fit. And the next step after doing this, we'll have to predict the values of the X test of the testing dataset. So what we will do is we will just get the Y predicted, and we'll get them how with the classifier dot predict method, and over here we'll set X test. These are the predicted values. So for example, if we print them, we'll see them as it is. After having the predicted values, just like in the previous algorithm, the next step in this whole process is to evaluate the results of the prediction. So let's just think page evaluating. Okay, just delete this. Okay, so there are several ways how to evaluate the algorithm as seen in the previous example. So we can first print the confusion matrix. There it is. This is a function from the scikit-learn matrix that will create a confusion matrix so that we can see how many true positive, true negatives we have, etc. So the confusion matrix of y, y test and y predicted. We just have to import it first. From scikit-learn matrix, import confusion matrix. There it is. Oh, this looks nice. After doing the confusion matrix, X train, Y train, We can print also the classification report, this which should be, I think, imported as well. The classification report will give us a lot of information for okay, it seems that none of the values actually was classified as none of the values was classified as anomaly, as we can see over here, which is quite bad. So that means that this algorithm is not giving the desired results because the points that are set over there are not we're not able, the 7 algorithm is not able to separate them with hyperlane. uh, okay, yeah, definitely none of them was classified as yeah, as we can see, we are getting a nice result for the accuracy, because 1100 1107 instances that were abnormal, that are normal, are pretty much all of them are classified as they should, but the metrics for recall are quite bad. Here they are. So yeah, let's continue with after doing the classification report, we can calculate the F1 score. I will have to import it as well. So learn metrics, import F1 score, and we'll print the F1 score for Y test and Y prediction. And as we can see, the F1 score is pretty much bad. So this is not a good result, because we have the recall probably a 0 over here. Don't know if we had made any mistake in the whole process. Let's run it again. Confusion matrix of Y test and Y prediction. Yeah, but it's really possible that the whole algorithm actually just gives us bad results because it's not fit for this kind of problem. Yep. Let's maybe try to let's try again to split the data set into something else and see what will happen. So xtrain. Okay. Okay, let's try again. See, maybe we'll get some other numbers, but xtrain, y train, y predicted. Pretty much still the same results. Okay, let's give it a try with some other support vector machine classifier. Let's maybe add a new kernel, which would be by default the kernel that is used is RBF, I think. Let's try it with poly. See what will happen in this kind of situation. Are we going to get an improvement of the results? Nothing. And now we are getting some instances are finally classified as anomalies, but let's see what we'll get now for the metrics. Yeah, now we had Now we have at least the F1 score is not 0 in this situation. We can try to balancing the data set as previously done in the logistic regression, and let's see what will happen in that kind of scenario. So let's add balance the data set. So we will just import this, the random oversampler, and create the object of type oversampler. And then we will create xres and yres, which will be equal to the oversampler dot fit resample, and we'll send x train here and y train. Okay, let's see now the count of the values in the yres. Let's see how many anomalies we have over there now. Values count, sorry, rank order of the words. Value counts. So now we have an equal number of anomalies and normal situation. This oversampling is just creating the it's creating an equal distribution, a balancing of the positive and the negative instances in the data set. So let's try the algorithm again. So I will just copy from above and see if I'm going to get an improved. So now instead of x train, this will be xres. Here it will be yres, and then we'll predict x test again, the testing values, and let's just print the f score after having this. So that's the most relevant metric that we could have. So let's see what will happen. We got a slight improvement. We got a slight improvement. Uh, let's now give it a try without this. Let's try it with the default support vector classifier to see what will happen. Previously it was 0. Let's see if this is going to improve it a bit. Oh yeah, actually we had quite the improvement now. While before, when it was with x train and x test, y test, sorry. Y train. So let's see what will happen now. Are we going to get something? Yeah, it's still 0. um, with the balancing of the data set, as we see, we got some improvement, 0.55. Okay, another thing when working with, as we previously saw here in the documentation of scikit-learn, um, when working with this kind of machine learning algorithms that required quite a lot of parameters, it's really hard to find the correct parameters. As you saw, I had to modify the kernel. I had to modify the C constant over here. There are a lot of other arguments like the degree, like the gamma value, etc., etc. For that case, we can make a grid search, which will take quite time to execute. So let's just add this as a text. Grid search for SVM. So this grid search will help us to find the best parameters for a given model. So when working with grid search, what we have to do is we have to define a dictionary. First, let's import from scikit-learn model selection. We can import the uh, grid search CV cross validation. So we already spoke about cross validation in the introduction presentation. Okay, before doing grid search cross validation, what we have to do is we want to decide which of the parameters are we going to we want to tune and find which one is the best of them. We can provide them as a list where in each of the dictionary we will state what we want to try to work. For example, I want to try it with we saw that we had some nice results with poly. Let me just copy one dictionary. So I want to try the kernel to be poly. I want to try some degree from the range from 1 to 9. I want to try different values of C and also different values of gamma. So these are the parameters that I want to try with the grid search cross validation. The scores that we are going to evaluate the models for are precision and recall. And next thing, we are going to iterate for each score in the scores list. We will be starting to create a classifier that would be grid search cross validation. Over here, this constructor expects the estimator that we are going to use. We are going to use the Savama SVC over here. And then it expects the parameters grid, that's this tuned parameters. Scoring also is expected, which will be, the scoring will be macro score. So what does this mean? It would be macro precision or macro recall, depending on which one is iterated at the moment. After having the classifier, we will fit the data, but we will now fit, let's fit the balance data set, because that showed us that we can have some nice, some better results. Also for the y values, they have to be a one-dimensional array again, so we'll unravel them again. Okay, and after doing this, we can print the best parameters for the classifier. We'll print the best parameters for the classifier. This will try all of the parameters over here. We can get the cross-validation results as well. We can get them as TV results, actually. The underscore. Yeah, and after it, let's predict let's evaluate the model at the end. Let's evaluate the model. So y predicted will be equal to classifier dot predict x test, and let's print also the classification report for the y test and y predicted, and also let's print the F1 score for the, again, y test and y predicted. Let's see what will happen now. Of course, we have some macro precision. Actually, it should be, sorry, it should be reverse over here. It should be first then, first this, then macro, I think. Let's take a look. Yeah, I think now it's starting to loading something. So this will take some while to execute. As we previously mentioned, this algorithm is quite slow, even when trying this all combinations. So there are a lot of combinations over here. 1 times 10 times 4 times 2. That's a lot of combinations that need to be tested and evaluated with both the metrics. So times 2 at the end. That's the whole number of combinations that will be evaluated with this grid search. As you can see, we are getting this exception warning over here. That happens because in some of the situations the model is just simply not classifying any of the abnormal instances the way it was doing it before. So that is why we're getting all of these exceptions over here. So we finally got some of the results over here, which are related for the. This was taking quite a lot of time, and it will take quite a lot of time more. So these are for when we are evaluating, when we are scoring the best method, the best model based on the precision, on the macro precision. So first we printed out the best parameters of the best model. They are when C is 1000, when the degree is 1, when the gamma is 001, and the kernel is poly, because we were trying with poly over here. And we have some results over here. Mean score time, standard score time, masked array, etc., etc., etc. The parameters that were being used, all of them here are stated, and the tests for each split, the test scores, there's quite a lot of here. But the most important for us is that this method has found for those parameters, it's giving up F1 score of 0.5059, which is actually not better than the one that we previously had, but yeah, but that is with the new parameters over here. So this is how you perform a grid search. As I said, this is taking quite a lot of time because we won't even wait for the other one because it's let me see what's the score that we're printing over here. So this is classification result, yeah, and the F1 score, because the whole SVM algorithm is quite time complex.